Order, as the speaker can no longer say. Thank you very much for coming. And someone's got a Land Rover with one of those snorkely exhaust pipes, which has got its lights on outside, if that's a problem. And also, can I say that the annual subs for this fine institution are sort of becoming sort of due. It's £20 a year, incredible value, or £3 a night. So if you could see your way to getting onto the website when you do next month or something, and there is a facility there where you can do the annual sub as well as paying for a meal. So I'm very grateful if you could do that. And so tonight, we've got a couple of questions tonight. Yep.
It's ringing a bit again.
Okay, I'll keep talking and see if that's any better now. How does that work? Any good? Perfect. And so tonight we've got a couple of questions tonight, one of which is, where is the universe? Which struck me as quite easy, and then I thought it probably isn't in some way, and then Jane tells me it is easy, so anyway, that should be all right. And the second one is, what can we see of it? Which obviously in Anglesey is absolutely nothing since August, since it's been raining every day since August, but nonetheless, in South Wales, where Jane comes from, it's a bit clearer. Where can you see it? What can you see? So Jane has written 3 books, writing another one on the elliptical orbits of Mars, and it's obviously highly clued up, having been given a telescope how many years ago?
2006, so whatever that is, 18.
18 years ago, it was given a telescope, and that has produced 4 books and a sort of late life interest in all these matters. So over to you.
Okay, well, good evening, everybody. We're going to think big, Ross Niger, tonight, and see if we can work out where the universe is. There we go. So what can we see in the sky? Well, we can see, which one's the light? That one. We can see clouds. We can see the sun, which is about to set in that picture. We can see some stars like that, and we can see the moon. So those are the kinds of things we can see. And let's have a look to see what I saw one evening, all within the space of just an hour. And all these pictures were me messing around with a new digital camera, taking time exposures just to see if I could get this wretched camera to work. Thank you. And I didn't use a telescope or anything fancy like that. So here's one shot taken with this camera one December night from my garden at 5:05 in the evening, and you can, if you're super perceptive, you can see a few stars on that, but what you can definitely see is 2 planets. Right. Yeah. And one of them's Jupiter and one of them's Venus. And if you were to look super closely at Jupiter, you can see moons around it. And you can take a picture like that of Jupiter's moons with just an ordinary camera. Nothing special, and you can see them through binoculars as well. Same night, a bit later, we know what that is, don't we? Yeah. And then a bit later that night, just here, wait a minute, it's wrong button, go that way. I've picked up just there, no, it's the wrong one, sorry about this. Back. There we go, there it is. There's a galaxy there that you can see, just about. Again, picked up with just a normal camera. So, in that night, we've picked all those things up. So, let's work our way through these objects and see what they are. So, what's a planet? I mean, this got topical a few years ago because Pluto got demoted from a planet. And feelings ran a little bit high about that. So there are two types of planet. There are rocky planets, and we live on one of them. Mercury, Venus, the Earth and Mars are rocky planets. And there are gas giants, Jupiter, Saturn, Uranus and Neptune. And how do I know they're there? Well, I took those photos, so that's how I know they're there. And we've landed spacecraft on 3 of those rocky planets, and we live on one. Do you know where the robot is? Mars, that's right. Yeah, and so Mars is in fact the only planet to be inhabited entirely by robots. That we know of, yes. The only planet in the solar system. What about the moon? Well, I don't know if you saw it tonight, but you could see the moon. It was almost as full as this picture. It's a very small rocky planet that doesn't orbit the sun so much as orbits the Earth. And the rocky planets all orbit the sun. So that's one of the criteria for a planet, is that it has to orbit the sun. And the moon, most of the other planets have moons, but the Earth's moon, compared to the Earth, is much bigger than the others. I mean, in fact, it's almost true that the Earth and the moon are twin planets. And so far, 12 people have walked on the moon. Who fancies going there? Yeah, a few hands going up there. And what's it like on the moon?
Dusty.
Well, actually, somebody said cold. Dusty, definitely. In fact, because the dust doesn't get eroded by air, it's very sharp dust. And that was quite a problem with their spacesuits. And so when they go back to the moon, that's one of the problems they've got to solve, is to make sure that the spacesuits handle the dust. But actually, there is cold at night for sure. But the ground that guy is walking on is above the boiling point of water in temperature. It's more than 100 degrees centigrade. And so their boots because it just gets the sun beating on it for 2 weeks with no atmosphere to tone it down. So one of the problems was that, they had this cooling system in their backpacks as well as oxygen. They had to keep the boots cool so that their feet didn't get burnt. The gas giant planets, these are, this picture to the left, you can see the 4 rocky planets. In comparison, the 4 gas giants, of course, are Jupiter, Saturn, Uranus and Neptune, and that's supposed to be Pluto out there. But these are much bigger than these rocky planets. And they have no solid surface. You can't land on those, even if you wanted to. The surface that you see there is gaseous. So, and why are they further out? Well, it used to be believed that the reason for that was because they're further from the sun. And if you brought Jupiter to where the Earth is, Jupiter's 5 times as far away from the sun as the Earth is. If you brought it here, all that gas would boil off. But as people have discovered planets outside the solar system, they've found that that's actually not true. There's something else going on as well. And that's a kind of subject of ongoing research as to why that is. And the reason they've discovered a lot of Jupiter-like planets first, of course, is because they're big and therefore easier to find. That's a group of stars called Orion. Again, that's me taking a picture with an ordinary camera. In fact, I took that one in South Wales last November. And so the belt in Orion is quite a familiar object and easy to recognise in the sky. That star up there is Betelgeuse, this yellowy one, so we'll talk about that a little bit. And that one down there is called Rigel, because its name is, this is supposed to represent a hunter in mythology. That's supposed to be the hunter's belt, that's the sword, and that's his bow. Just there, like that, and there's his left arm going up I mean, do you fire bows like that or like that? I don't know. I'm left-handed, so I get confused. But anyway, he's firing his bow. That's supposed to be the idea. And the name Beetlejuice, it looks as though it's spelt in French, but actually it's a corruption of an Arabic word for armpit of the hunter. And Rigel, the word in Arabic is rajul, which means leg. And that object just there is a nebula. You can't, at least I can't, quite see that it's a nebula just by standing and looking up. But with binoculars, you can certainly see that it's not a star. And that completes my tour of the sky. The main objects we've seen are the moon, the planets, the sun, the stars, nebulas, and galaxies. And I know
What's the difference between a nebula and a star?
a nebula is a cloud of gas. In fact, I'll come on and talk a little bit about nebulas. So, can I park that question,
Yep.
please? And all those photographs, except for the one of the astronaut, were taken by me. So that's how I know it's true, because I've photographed it. Now, with planets, if that's the starry background is here like this time you can see the stars. Now, relative to the starry background, planets move. I mean, I have no idea how to pronounce ancient Greek, but Aster planetes meant wandering star. Aster was star, obviously. These are, how far apart are they? Nearly 3 days apart. And the planet has moved relative to the starry background by that much. And what we're seeing is a combination of the planet's orbit around the sun and the Earth's orbit around the sun, because they've both moved in that time. And what I did was I took 2 photographs and then moved them until the stars were in front of one another. And the stars are so much further away that any movement in them is just not detectable on a 3-day time scale. So what's a star? Or what's the sun? Who knows? Yes? The sun is a star. What else? Sorry?
Nuclear furnace.
Yep. That's right. It is. So it's a giant ball of really hot gas. And it's 1 million times as big as the Earth, but it's not solid like the Earth. And it's, as the gentleman says, it's a nuclear furnace. It's on fire, and what's driving the fire is nuclear power. So, I mean, they've had a few nuclear power stations around here, haven't they? Well, there's a big one. And the heat from that fire, nuclear reaction is what keeps us alive. So you obviously don't want to get too close. And NASA have launched a probe called the Parker probe, which is getting the camera peeps through a pinhole in a heat shield, so that basically they're getting as near as they dare to it, and presumably eventually this thing will get vaporized. But it actually is quite difficult to go to the sun, because the Earth is orbiting the sun at a speed of 19 miles per second, and it takes obviously 365 and a bit days to get round. And so you've got to build a rocket. If you want to go to the sun, you've got to basically deorbit the rocket from around the sun. So you've got to fire it at 19 miles a second that way. And we can't build a rocket that powerful. And then for that reason, there's no danger that the Earth is going to fall out of the solar system and into the sun. Now, the stars in this photo are also big hot balls of gas, just like our sun, but they are a really long way away, so far away that we can only see them at night. And one of my favorite comparisons is that the distance between 2 stars typically is like having 2 grains of sand 1.5 miles apart. And so that's how much space there is, with the result the stars basically don't collide. Because they're too far away from one another. And that star just there is called Betelgeuse. It's much bigger than the sun. And in fact, Betelgeuse is so big that if I said the sun was 1,000,000 times the size of the Earth, well, Betelgeuse is 1,000,000 times the size of the sun, or something like that. It's just huge. And stars are made in nebulas like that one. And nebulas, a nebula is a very thin cloud of gas. I mean, the gas is so thin that we can't, with vacuum pumps, make a vacuum that, they talk about hardness of vacuums. We can't make a vacuum that hard on the Earth. So this thing is enormous. And it's probably got 1,000,000 times the mass of the sun or thereabouts in it. And I know it's there again because I took that photograph of it. It collapses to form, under its own gravity, to form stars. And it needs to be that big because otherwise there isn't enough gravity to overcome the random motion of the molecules and collapse into stars. But it's a very inefficient process. Maybe only 1% of the matter in that cloud will actually condense into stars. So galaxies, stars are not evenly spread through space. They're collected together in galaxies. And this galaxy is called the Andromeda Galaxy. It's the one in that earlier photograph. And that's how many stars it contains. And each one of those is 1,000,000 times the size of the Earth. So I hope you're starting to get a sense that this thing's quite big. And it's in fact something like, we live in a galaxy called the Milky Way. The Andromeda Galaxy is sort of twice the size of the Milky Way, something like that. But it's the nearest big galaxy to us. But actually, I've got it the wrong way round. In the early universe, gravity, after this event which gets called the Big Bang, if you've got an even distribution of gas and you get a slight fluctuation in the evenness, so that there's a region with a bit more density, gravity will start to pull it together. And so an even amount of gas in this early universe is not stable. Gravity will clump it up into lumps. And these lumps became our galaxies. And what actually happens is that you need a galaxy to make stars rather than the other way around. Stars don't make up galaxies because there's also a fair bit of gas within galaxies, not in stars. And what you can see, 10 billion years ago, most galaxies were like this one that I'm showing here. The nucleus of the galaxy caused matter to circulate, and the nucleus is kind of, I better use this laser thingy, hadn't I? The nucleus is there, the brightest point. There will be a giant black hole there. A black hole is something so massive that nothing can escape from it. Because one of the rules that Einstein discovered was you cannot go faster than the speed of light. And to escape from a black hole, you'd need to travel faster than light, and you can't, so you can't escape. And you get an effect, it's called gravitomagnetism in the jargon, and don't ask me to explain that because we'll be here for about 3 years. But it happens, and it's pushing this matter out there like that, and that's the sort of the plane of the galaxy there, where all that dust is. And all this faint luminous matter is stars that it's made. So what this black hole in the middle does is, we know it's a black hole because the matter close to it, in order not to fall in, has to orbit it at close to the speed of light. And one of the things you can do with the technique called spectroscopy is you can tell how fast stuff is moving towards or away from you. So you can tell that it's moving that fast. And that's how they detected these black holes in the middle of galaxies. And the result of all this activity is that it churns material around the galaxy. And the precise way, that image is not just visible light. This stuff being pushed out there is a radio image. there, and some of it is taken in the X-ray as well. And a few galaxies like this one still have these active nuclei that churn matter around the galaxy, but most of them, the active nuclei have kind of fizzled out by now. And so 10 billion years ago, there was a lot more star formation than there is now. We are living in a post-peak star formation era now. So stars make galaxies. Sorry, galaxies make stars, not vice versa. Now if I change the subject a little bit, here's an exploding star caught in the act. This galaxy is called the Pinwheel Galaxy. It's about 20 million light years from us. So you can't go there in a rocket because you need to live 20 million years, and even I'm not that old. But not quite, thank you. Just there, that's not there in this picture. So that's appeared in the meantime. And I heard through the Bush Telegraph, which of course these days means social media, that this thing had been found. And so I got one of the first photographs of it in the UK and got my 15 seconds of fame because it got published in BBC Sky at Night magazine. And then I got a phone call from, because they put it on their website at first, it eventually appeared in the magazine. And I got a phone call from somebody saying, I'm a researcher from the BBC, can we come round and interview you while you're taking a photograph of this thing? So I said, well, yeah, that's fine, but you realise it'll be at 1 o'clock in the morning. Oh, that's not a problem. So anyway, next thing I know, there's this guy from the BBC put a microphone in my face, saying, tell me all about this. And I'd kind of forewarned the neighbours that there might be a bit of noise in the backyard that night, but they didn't seem bothered. So, and in fact, it's an edition of what's it called, Science in Action. I believe it's still on their website. Change subject. How are atoms made? Well, everything on the Earth is made of atoms. We kind of learn that at school. But these atoms are mostly made when very big stars explode, like that one that I just showed you. This thing was so bright that it's as bright as the rest of the galaxy, and I tested that. I turned the brightness on my camera right down to see what disappeared, and everything of the galaxy, except this nucleus, the bright spot in the center, that was the only bit that was as bright as this star at its peak. So this star explodes so violently that it outshines the other 100 billion stars in the galaxy. That's quite a bang. And most atoms are made in this explosion, or other explosions like it, and then stars and planets condense from the resulting nebula. The exception to that is that hydrogen atoms and most helium atoms, in fact, came from the Big Bang at the start of the known universe. But every other atom beyond that, lithium, beryllium, boron, and all those other things that you don't learn in the periodic table, all came from supernova explosions. So, and the thing is that the material of the Earth can only exist because the sun's a second generation star. There is some hydrogen in us, but we're made of carbon and bits of calcium and this, that, and the other. And the rocks in our planets, what's the Earth made of? Iron mostly, with a bit of silicate rock and oxygen and aluminium, I think is the next most common element. So all these things were made in supernova explosions like that one I just showed you. So it really is true that we are all stardust. Now, these galaxies sometimes collide with one another. And here's a picture I took in January this year showing two galaxies. And the result of the interaction is that the spirals got amplified in this spiral galaxy here. But the other galaxy there just got ripped apart. And people have done calculations to try and work out what happened. And it seems as though that galaxy was about 4 times as big as that one. So that one kind of survived and that one didn't. And the blue areas are areas of rich star formation. And we know that because blue stars, a yellow star like the sun, has an expected life of about 10 billion years. And it's something like halfway through that life. And it will eventually die spectacularly, but don't wait up, it won't happen for a while yet. But blue stars live for 1 to 10 million years, so that's between 0.1% and 1% of the life of a star like the sun. So we know that the ones that we see, and the blue stars are much brighter, much more massive, and so they burn through nuclear fuel a lot faster. So they live fast and die young. And if we see blue stars like we do in the lower of those 2 galaxies, we know they have to be young stars. So we can kind of tell where the star forming regions are. But the other thing that we can see pretty well in that is with this brown stuff is dust. And if you look closely, the dust is on the inside of the spiral arms. Like that there. And you need, dust is very, very finely distributed, tiny, tiny particles of the kind of stuff that's on the Earth, silicon rock and bits of iron and things like that. So it's basically the debris of earlier supernovas. And you need these to act as a kind of catalyst for the gas to condense on. So if you've got dust around, that also helps star formation. So we can kind of tell where the young stars are in a galaxy, but theories of how stars form in galaxies are, they're not by any means complete. I mean, if I gave you a talk now on the life of stars, and my ghost were to come back in 50 years' time and give you another talk, it would basically be the same talk. But if my ghost were to come back and give you a talk on galaxies, it would be quite different from what we know about galaxies today. That's really at the cutting edge of what we know. So we know it has to happen, but we don't really quite know how. Now, galaxies themselves, as well as bumping into one another, well, they didn't really bump into one another, it's just that their gravity caused them to interact. They tend to group together. And this is a group in the constellation of Leo, so if you're around 2 o'clock in the morning, you could in principle see that group. And I took that photo. I actually took 3 photos and put them together in a collage of those galaxies. So that's a group of galaxies. And we at the Andromeda Galaxy and one other galaxy called the Triangulum Galaxy are the big galaxies in the local group of galaxies. But this is a different group. And then the galaxy groups tend to cluster into what get called clusters of galaxies. And the Virgo cluster in the constellation of Virgo, and again, if you're around at 2 a.m. in the morning and it's clear, you can see this part of the sky at this time of year. It'll be in the skies in the evening by April, May, that kind of time. That's the center of the Virgo cluster. And in fact, the Virgo cluster is a huge cluster of galaxies. I mean, on my high quality computer screen at home, I can see over 30 galaxies in this image. And you can see a few there. And one of the things that happens at this, so we're all citizens of the Virgo cluster of galaxy, no matter whether we're EU citizens or not, whether we like it or not, we are citizens of the Virgo cluster. Is that these galaxies at the center, and especially that one, because that's the biggest of them, they are not spiral galaxies. I mean, those 2 there are spiral galaxies of the type that we all kind of know about, because they're fun to take photographs of. These elliptical galaxies are a bit boring to take photographs of because, they're just lumps. So you don't see so many photographs of those. But they tend to exist at the center of big clusters of galaxies. and it's their gravity that is kind of dominating the pull in. Now, just for fun, even though it never goes to that part of the sky, I've plonked the moon in the middle of that picture, just so that you can see the scale of that cluster of galaxies compared to what the moon looks like in the sky. Of course, the moon is 1,000,000 times brighter than these, and I'm not just saying 1,000,000. I did actually sit down and do the calculation, and it is about 1,000,000 times brighter. So, there's groups of everything, and if there's 2,000 galaxies in this Virgo cluster, which is about what people have counted. Remember I said there's 100 billion stars in each. So that means there's 2 trillion stars in the Virgo cluster. We're kind of talking big.
How far is that roughly?
Whoops, I can't find the laser button. That's the laser button. That one's about 60 million light years from us. And those will be a similar distance. I mean, that group is called Markarian's chain. And Markarian was an Armenian astronomer in the Soviet era who did some measurements of the speeds at which these things are moving. And he found that the Markarian chain is co-moving, so that's why it was named after him. Now, you've heard of the Hubble Space Telescope. It's up in orbit. Well, they did a count. What they did was pointed it at a part of the sky which was known not to contain many nearby stars to kind of distract. And they found from this count that if you multiply it up to get the whole of what's around us, there would be 130 billion of these galaxies there. And each has 100 billion stars, each about 1,000,000 times the size of the Earth. So the known universe is a very, very big place. But where is it? Anybody tell me? Exactly. It's all around us. So that's the answer to the question, where's the universe? Yeah. Did somebody say infinite? Well, it might be. It might be, and some of the theories about what caused the Big Bang.
Big Bang didn't exist.
Well, okay, fine, you're entitled to your opinion on that. But I think the consensus amongst people who are experts in this is that it did happen. And we can tell that the universe has aged, and the galaxies have matured and so on. So I think there is pretty solid evidence that something happened, even if we don't know what. So it's all around us, and we are part of it. And the best possible explanation is that space is being created between the galaxies, because they're all known to be receding from one another. And that's how you work out that if you run the movie backwards, they were all in the same place at one time. And the thought is, I can see this gentleman disagreeing with me, and fine, you can have the microphone in a minute if you want. But so that's where the idea of it all being in the same place came together. And most of the models show that if you assume that space is what's doing the expanding rather than the galaxies moving through space, that's how the Big Bang Theory has been put together. But it's all speculation. We haven't got an earthly chance of working out, when it was all very close together, we haven't an earthly chance of working out what the physics was like there, because we cannot reproduce it in laboratories. The claim with the Large Hadron Collider, that big thing that found the Higgs boson and never found anything else in Switzerland and France, the claim with that is that the energy with which they collide protons together reproduces conditions going back to a millionth of a second after the Big Bang. So that's as far back in time as we can go towards the event itself. I mean, there are theories of what happened, 0.30 zeros and 1 seconds after the Big Bang event, but why was there a Big Bang? We don't know. And it's very hard to find out. And there are also, there are theories that actually people measured the rate at which galaxies in these big clusters were moving towards one another. And there was a guy called Fritz Zwicky did it in the 1940s. And what he found was that the luminous mass, the stuff that's bright, was nowhere near enough mass to cause it to collapse at the rate it was. Most people think there's some stuff called dark matter that we can't see there. And I would say 90+% of professionals think that. But there's another, somewhere up to 10%, I could quote an exact figure, who think that actually what's going on here is that we're using the best theory of gravity we've got, which was developed by Einstein 100 years ago. And that works. We know it works on a stellar scale. If you've got binary stars, we know it works on a solar system scale. I think we even now have tested it out to a galaxy scale, but on bigger scales than that, there's a question mark about it. And it may be that there's a law of gravity yet to be discovered that can explain away dark matter. People also talk about dark energy as being the repulsive term in Einstein's law of gravitation. Now, the thing about this dark energy is that the prediction of how strong it would be from Einstein's law of gravity is wrong by a factor of 1 with 120 zeros after it. So that holds a world record for the most wrong physical theory ever. And therefore, I think by the time all this is sorted out, physics will look very different from what it looks like now. And with that, I'll conclude.
Thank you very much indeed. Can you go back to slide 31? Thank you very, very much. We may just keep it dark for a moment. Just a couple of slides I'd like to just ask you about. You took that photograph.
Yes.
How on earth did you do that, and how massive is your camera?
The camera is not massive. It uses a similar. It's a digital camera, as they all are these days. The chip in it, I think, was developed for high-end digital single-lens reflex cameras. And that chip, you put it in this camera, and what you do is you cool the chip and you can control it. You need a computer to drive it. You can control it. So I set the temperature on the chip to about -15 degrees centigrade, and it'll hold it there pretty well, because that means that all the electronic noise, I mean, you don't realize it, but when you take a picture with a camera like that or with your mobile phone, there's a lot of stuff goes on before that image appears on your screen. But if you take a mobile phone picture, I mean, if you took one in here now, it's so much brighter than the noise in the chip that you don't need to worry that much about it. With this was exposed for 6 hours, I suppose. Okay. So over that time scale, you do have to worry about the noise in the chip. So you cool it, and you also take a lot of other frames, like dark frames and flat frames and bias frames and stuff, so that you can subtract off all the effects of the chip and get the image. And you then put it in software. I mean, I use a piece of software called PixInsight, which is a kind of fancy version of Photoshop specialized for astrophotography.
And are you the only person to have captured that moment, or are there other people doing?
Oh, there's enough people that there's quite a sizable market for these astronomy cameras.
So someone else will have got a picture like that?
Oh, yeah.
Yeah.
Yeah. Okay. Yeah, I mean, there's nothing particularly special about that picture.
And can I just take you back to the other one, which had the where you had the time lapse in February, when you had those two pictures going back? Yeah, there. So that feature that came onto the picture in May. What is it?
It's an exploding star.
But it's the line, the straight line.
Where was it?
Yeah.
Oh, the lines are where I've marked it.
You've marked it there. I see. Yeah.
Yeah, I put those in with.
Yeah. Very good. Now, I'm sure there are lots of questions. That's an extremely interesting talk and very amazing what happened when you were given a telescope 18 years ago and the knowledge you've picked up since then. So have we got any questions?
Jane, thank you. 2 questions, please. The first is, can you explain what delineates a galaxy? What's at the edge? What stops it becoming something else?
That's a good question, but yes, gravitation is part of the answer. It's held together by gravity. But in fact, with those spiral galaxies, they're also rotating. So it's a trade-off between the rate of rotation tending to push it out, centrifugal force, and gravity pulling it back in. What causes the size of it is thought to be random fluctuations shortly after the Big Bang, which caused this gas to clump up.
Okay, thank you. Second question.
We have no detailed picture of that.
I'm trying to compute it and trying to pretend I'm clever enough to understand, but I'm going to go away and think about it, but thank you. Second question, you obviously spend a lot of time looking out there, and the numbers are amazing. Do you sit there when you're looking, thinking, there's life out there, there's something else?
I think the chances of there not being other life out there are minimal because there are just so many stars. Do I think we will ever contact them? No. Because first of all, at the rate, we're either going to nuke ourselves or fry the planet or something. So, there will be a post-human era on the planet at some point. So, if our civilization lasts another 1,000 years, it's going to be a miracle. So you've got this window. Well, if you say from the start of the industrial age, that was 200 years ago in round figures. So if an alien civilization, the kind of things that we can just about do in principle now for stars, planets in other solar systems, is we think we know what chemicals to look for in the atmosphere, and we're beginning to know how to do it. So you look for industrial pollutant type chemicals. Right. And you also look for chemicals that are typical biosignatures, water being the most obvious one. So if somebody else is doing that and looking at us and finding those pollutants, they can only have done that from 200 years ago. So for them to pick up that signal, they've got to be within, and get a signal back to us in some way. They've got to be within 100 light years of us. And we know that there are 12,000 stars within 100 light years of us or thereabouts. And some of them have planets on. But so many improbable things had to have happened for a civilization to evolve on the Earth that actually the chances of finding one are well under 1 in 12,000. And therefore, civilizations will never contact one another. And I'm sorry if you like Star Trek, but that's kind of the way it is.
Question here, yeah.
Sorry to go on about the Big Bang. It's just a thing I have about the Big Bang. The problem with the Big Bang is what happened before it and what happens after it.
Well, time was created in the Big Bang, so there was no before.
Well, there we are. There was no before. That's a wonderful thing to imagine, isn't it? No before. But the trouble is, it's a consensus.
Yes, but time doesn't elapse absolutely. We know that, for instance, on the surface of a neutron star, time only elapses at 80% the rate it elapses here on Earth.
Yeah.
So it's not an absolute.
Can I just mention somebody asked about life. The most interesting experiment that's going to happen shortly, they're going to send a tiny spaceship to Alpha Centauri. Now, if you know, Alpha Centauri is only 4 light years away. Yeah. It's impossible to go there by any means that we have because the distance is vast. But you can send a tiny spaceship there. What you do, you put a solar sail on it and you fire a laser at it. The laser's moving at the speed of light, and that little spaceship will get to Alpha Centauri traveling at about 20% the speed of light. It will only take 20 years to get to Alpha Centauri. it could then photograph Alpha Centauri and send a picture back to Earth. So in 25 years, we could have a picture of Proxima Centauri, which is the planet going around Alpha Centauri.
It's a star, but yeah.
Yeah, Alpha Centauri is a star. Proxima Centauri
Is a star.
is a planet.
It's a
one
star.
Of the,
It's
it's
burning
one of the
nuclear
double
fuel.
stars, but it's got planets going around it.
Yeah.
It's got a lot of planets going around it. So we could get a picture of a planet going around Proxima Centauri in about 25 years.
Well, plus the time it takes to send the signal back. I mean, do you know
Well, it's
what?
4 years.
The time it takes to send the signal from, the furthest space probes we've sent out, like these Voyager ones, which went out to the outer solar system and now moved beyond the solar system. In order for us to pick up the signal, they have to send the image back so slowly that it will take you more than 25 years to transmit a photograph.
The image will travel at the speed of light, which takes 4 years
Yeah.
from Alpha Centauri.
But the rate at which you can send it out is much less than that. It's much less than a dial-up modem.
I've just told you that the spaceship carrying the camera,
Though the signal, once it's sent, will travel at the speed of light, sure. But you can't send all those pixels from an image even as fast as a dial-up modem. So it'll take you forever to send it back.
There's a question in the middle at the back there. Yeah.
Thank you. Thank you very much for your talk. It was great and really fascinating. I got 2 questions. The first one might be a bit of a stupid question, so bear with me.
There's no such thing.
But you're talking about atoms being formed.
Yeah.
So in these galaxies and nebulas that are far away, let's say there is an alien planet or civilization or something, would they have a completely different periodic table to the one that we have?
No.
Or are they forming just...
No, we
everything that
know
already
from... we use a tool called spectroscopy. And using spectroscopy, you can examine atoms far away. I mean, you have to have enough of them to be able to see when they're millions of light years away. But what we know from that is we can go back quite early in the life of the universe and see that the chemistry is still the same as it is here on Earth.
Right.
Okay.
So, yeah, they wouldn't
Yeah.
have a different periodic table.
Okay, cool. And the second question is, how important is something like what you're doing, and obviously people like NASA who are doing it on a gigantic scale, how important is photographing the universe for discovering whether dark matter, or what dark matter is, or whether it is even there?
Crucial.
And is it more important, do you think, than the maths?
No, they're about equally important. But you raise a very good point, which proves that there is no such thing as a stupid question, which is that observation, as long as you can agree on what the observation is, which is a far from trivial state of affairs, observation always trumps theory. For instance, the structure of the solar system. It was Galileo who was at least the first great scientist. There were a few other people as well, who published results on looking at the planets through a telescope. And what he discovered by this observation showed beyond a doubt that, for instance, that Venus orbits the Sun, not the Earth, as had previously been thought, and things like that. And at every step, Hubble discovered the expanding universe, not by theorizing, but by photography. And Einstein, who thought was a theorist, never did any experiments, and he thought it all had to be static, but then Hubble showed that it wasn't. So the observation triumphs the theory.
If you just go further, just the other way, actually, put the mic. Is that Roger? Yeah.
I'm going to try a stupid question. See how stupid I can. Gas giants.
Yeah.
What gas?
Hydrogen and helium in Jupiter and Saturn. In Uranus and Neptune are blue because there are other gases which are collectively known as ices. Water ice is one of them, oxygen with 2 hydrogens. But you also get nitrogen with 3 hydrogens around it, which is ammonia. And you get methane, which is a carbon with 4 hydrogens around it. And collectively, when they're cold, they're called ices. in the jargon. And so those are the chemicals that make Uranus and Neptune blue.
Wow. And B, what, when you fall into a black hole, because you can't escape from a black hole, can you?
Correct.
Call
That's
me
correct.
naive. But where do you go when you fall into one?
Well, that's a very good question. With a star-sized black hole, as somebody shouted out from over there, you get this phenomenon called spaghettification, where you get stretched to death long before you reach the black hole, because the gravity where your feet are is stronger than the gravity where your head is, so the gravity will actually rip you apart. Okay, with a black hole the mass of 1 million stars, like the one at the center of our galaxy, that doesn't quite happen. You just basically, 1 minute you're outside it and the next minute you're in it. And you would survive that. But some really, really weird stuff starts happening once you're inside it, one of which is that space and time swap roles.
How does that look?
See, I knew it was a good
Weird.
question. Right. Thank you.
Can you explain what that means? Space and time swap roles.
That's correct. Well, in the theory of relativity, which is what you need to predict the existence of a black hole, space and time adjust themselves so that the speed of light remains constant. Okay, which is different from Galileo's, what gets called Galileo's theory of relativity, where distances and speeds are constant. But it's kind of a long story, and we could be here all night with this. But in the 19th century, people like Faraday worked out laws of electricity and magnetism. And then along came a guy called James Clerk Maxwell, who was quite a smart doc, in fact, probably one of the smartest there's ever been. And he produced a theory unifying electricity and magnetism, which he wrote down as I can't remember if it's 21 or 24 equations, but rather a lot of equations. So it was pretty complicated to get your head round. Then, a bit later, a guy called Gibbs, who was most famous for his contributions to thermodynamics, but he looked at Maxwell's equations and figured out a way called vector notation to reduce them to 4 equations, which then become kind of manageable. But buried in Maxwell's equations was this idea that the speed of light had to be constant. And the idea of electromagnetism, and it was discovered by a guy called Hertz, that electromagnetic waves, as predicted from Maxwell's equations, exist. But they didn't know what they propagated in. They came out with this idea of ether. And then in America, a guy called Albert Michelson figured out that because the Earth is moving, there's a 1 part in 10 million difference between the speed that you would observe light going in the direction the Earth moves and at right angles to it. So he did this. He thought he could do an experiment to measure this 1 part in 10 million, and he did. And he got a null result. He didn't find it. And, you can imagine he had to bust a bit of a gut to get to 1 part in 10 million with this experiment, so he had a nervous breakdown. But he kind of came back from that and collaborated with another chemist called Morley, or a chemist, because Michelson was a physicist. And so it's now known as the Michelson-Morley experiment. They did it again, and again they got the null result. So the last line in the paper says, the hypothesis of the ether is thus shown to be incorrect. So there was a puzzle there. Why was that? And it was Einstein who eventually figured out that if you hold the speed of light constant and adjust the rate at which time elapses, and if it comes to that, adjust the distances between things, then you can explain why the speed of light is constant, and that's known as Einstein's theory of relativity.
Well, that is such a good answer, Jane. Please don't test me on it. And anyway, the third part of my question, C, is what type of cheese is the moon made of?
Well, the green cheese is not green, the colour green. What green cheese means is you use the same terminology for things like plaster as it dries and concrete as it dries. It's not very hard to start with, and it hardens. And the state of not very hard, immature cheese is called green cheese. Just the same as it's called green concrete and green plaster.
I love it. I love it. Touche, pussycat.
I do want to just ask you, this astonishing amount of understanding and knowledge you have, was this all, because you said you did an MBA, business degree, before you got this telescope.
Yeah.
So is all this...
I already had a PhD in physics.
Oh, you did, right. So you were formally trained
Yes.
in a lot of this, and then later on you got
Yeah.
interested. Okay.
Jane, so Roger asked my question about the gas giants, but
Yeah.
I have another question,
Right.
which is, so the robots that have been exploring Mars,
Yeah.
recently, most recent one was a little helicopter.
Yep.
Now, how does that work if there's no atmosphere on Mars?
The atmosphere is about 1,000th as dense as the Earth's atmosphere. So basically, the rotors had to go fast enough to deal with this very low density atmosphere, and of course, the thing had to be super light.
Yeah.
It's about a third what it is on Earth. Yeah, that helps.
So, right, okay, very good. I loved your talk, thank you.
You're welcome.
There's a question here.
Yes, thank you for your talk. That was really fascinating. Roger asked my question about black holes, but I still struggle to get a picture in my mind. I understand that nothing can escape, no light can escape from a black hole, and I now understand that it messes up space and time, and you come out of it, you know, stripped and stuff. But in my understanding, everything that takes in something evacuates something at the other end.
Well,
And
that's,
what do you end up with? Dark matter or something?
well, that is a very good question. What Hawking discovered was that the one escape mechanism you can get, which was discovered 100 years ago by the likes of Schrödinger and company, and Heisenberg and all those people, and in particular a guy called George Gamow, was that you get a phenomenon called tunneling, where the thing about quantum mechanics is that which is the great theory of the 20th century besides Einstein's theory of gravity, the two theories cannot be made to match up. Nobody knows how to do that. And all sorts of people, very clever people, including Einstein, tried and failed. But you get this phenomenon called tunneling, where there is a probability that the particle is held captive by whatever potential energy is there. But there's also a very low probability that it's somewhere way outside it. Okay, and that's called tunneling. And the first phenomenon where tunneling was discovered was radioactive decay, alpha decay of atoms. That was shown to be tunneling. And in principle, we know that the matter around a black hole is atomic and therefore, or subatomic, and therefore quantum. So in principle, you can get a little bit of quantum tunneling out of a black hole, only a tiny amount. And that's called Hawking radiation, because Hawking was the one who discovered it. And a black hole, the mass of this drink, will evaporate by Hawking radiation on a timescale less than the lifetime of the universe to date. Pachi, our friend over here. So you don't get black holes that big. But a black hole, the mass of a star, it would take, for it to evaporate through Hawking radiation, would take much longer than the life of the universe. Cheers.
Yeah.
So thank you very much for your fascinating and boggling talk. I can fully understand the concept of the expanding universe starts from something very small, however boggling it might be, with everything flying out in every direction. But why, when it's all started flying out at these super speeds, why do galaxies then coalesce with one another?
Because galaxies, Well, if you understand why it all flies apart, send your answer to the King of Sweden and claim your Nobel Prize, believe me. Because, it's not well understood. People have some understanding of a phenomenon called inflation, and if you want the lecture on inflation, come back 36 times and I'll just about have explained it to you. I barely understand it myself. You see, the thing is, space was created as well at the Big Bang. So, and space is still being created as these galaxies, the distances between these galaxies get greater. Why is that? I don't think we really know. This is just some of these kind of, edgy theories of gravity that people are exploring predict this phenomenon. But, it's at the cutting edge of our knowledge and ignorance, so it's not established science yet.
I think, thank you very much. I think when I said I understand it, not that I understand the reason, but I understand that's what the theory is.
Yeah.
Yeah.
But
you.
don't think of it as exploding into space. Think of it as space being created between them.
Okay, let's go to the back and then.
I'm going to ask my very dumb question. Your wonderful photograph of the spiral of a galaxy.
Yeah.
Can I be stupid enough to ask which way that spiral is spinning? Is it expanding by going clockwise or reducing by going anti-clockwise?
Oh, it's the other way around, isn't it?
Because I thought you
mean
said
like
that
that?
galaxy. Yeah, didn't you say galaxies are expanding?
We don't know. This is one of the questions that people are actually trying to address currently. Is the expansion of space detectable on a galactic scale? And the answer is we don't yet know.
But can't your time delay photographs show that?
No, because it doesn't.
Because it's just too short a time.
Yeah, I think that's the answer. But one of the ways that people are looking at it is, I read a paper recently, a fairly recent paper, where what somebody had done was, one of the puzzles is that the brightness of the sun early in the life of the solar system was kind of anomalous and people can't explain that. And this guy said if you assume that the space is expanding within the solar system at the same rate as the overall expansion of the universe, you can explain away why all the phenomena that required the sun to be brighter than it is now go away. So that's a theoretical, not an observational argument for why the solar system is expanding at the same rate as the rest of the universe. But there's no observation to back it up, so we don't really know.
Because it looks like it would be reducing if it was going anti-clockwise. But then I'm only looking at
that's just because
plane.
of the direction you're looking at it.
Yeah, so
if you were on the other side of it, it would be going the other way.
Yeah. Wow.
Yeah, it's like if you put
a helix,
an LP record on a gramophone. From the top, it looks as though it's going, which way is it? Clockwise. And from the bottom, it looks as though it's going anti-clockwise.
Yeah, good point.
That's theoretical. You never observed.
No.
Was there a question? Who else has got a question? There's one. Yep, there we are. Yep.
Again, could I just reinforce our thanks for a very interesting talk. We keep talking about expansion.
Yeah.
And obviously, I suppose the theory is that, from without wanting to be too controversial, the Big Bang, everything is expanding.
Yeah.
Will it continue to expand ad infinitum, or at some point will gravity start to take over and contract back together?
That question was debated from the emergence of the Big Bang Theory in about 1945, thereabout, plus or minus a bit, to about the year 2000. People debated that. And during that time, people were able to measure the recession speed of galaxies further and further away. And which means going back in time. So because the light has to travel at a constant speed. And what they found by doing that is that the rate of expansion of the universe must be increasing. So it looks from our current state of knowledge as though it will expand forever.
interesting, but thank you.
I think it's a question again.
So I'm still trying to get my head around the sort of space and time swapping roles, but I'd like to try and bring it back to something a bit more comprehensible or comprehensible. So, you know, you're taking photos and you're going to have to deal with light pollution. You've got to deal with the fact that you're going to have a noise on the chip. How much of an issue is like pollution in space? You know, like satellites, things that we've put out there that are getting in the way. Is that going to like make a
They're a
bigger
blinking
issue for
nuisance.
us? Sorry?
They're a blinking nuisance. Because the number of them is about to explode in the sense that there were maybe a couple of thousand in the year 2020. By the year 2030, there's going to be like 450,000 of them. So they're a flipping nuisance. The part of the story about how I took that picture that I didn't tell you was that over those 6 hours, I take 60-second frames and then use software to add them all up to get my 6-hour exposure. So if there's a particularly bad trail on one of these, I reject it. Okay, but the software has got some capability in it to recognize straight lines and basically replace them with black. So
Straight line being
a satellite trail.
right.
So the software can remove the worst satellite trails. And I think, especially, one of the things that happened as a result of the pandemic was that people, astronomy, amateur astronomy mushroomed hugely over the pandemic because it was one of the few things you could do while you were still locked down. It was kind of the perfect lockdown hobby. And the computer programming types started to use AI to find methods to process these images. And there's some AI gone into processing that, for instance, to make the stars look nice and round, and to remove noise from the image as well. That's done by AI these days. So I think what will happen, certainly for amateur astrophotography, is that over the next few years, as this problem gets worse and worse, is that the AI used in photographs will get better and better at detecting satellite trails and removing them. That's not to say that it's not going to be a problem for professional astronomers. It's a real problem for them.
So one of the things that you showed was a picture that had added photographic results from different parts of the spectrum. And I was just wondering whether you could explain how those spectrums work and what it is that you... My understanding is that some of it's not visible, so some of it's the visible
correct.
spectrum, and so just wonder whether you could just talk us through that.
Laptop. Have we got an internet connection on this?
Probably not.
Yeah,
Okay.
no, you should.
Right, let's see if we can come out of this. Yeah, okay, well, I'll ask you a question what I'll try and do is find a particular Wikipedia entry. So, where's your internet browser on this?
It sounds much easier than all the other questions, but I'm not sure.
Well, it's a Windows PC, isn't it? So let's look for... No, there isn't.
Edge. Yeah, Microsoft Edge.
Oops. Right, there we go. Well, I'm not interested in your other internet searches, so let's start a fresh page. What do we do? We do that, don't we? Yep. Right, yes, continue. Right, now, let's search or enter a web address. Wikipedia. Wikipedia in English, that would help, wouldn't it? Wikipedia. Right, where's the search? There it is, yeah. radiation. There we go. The diagram I want might be on this. That's what I'm hoping. How do I scroll down with that one, don't I? There we go. This diagram here is what I want. So if I click on it, it might even fill it. There we go. You can see that, can't you? Right. Electromagnetic radiation has a wavelength. And there's the wavelength going from a nanometer is a billionth of a meter. A micrometer is a millionth of a meter. A millimeter, which is somewhere there, is a thousandth of a meter. There's a centimeter. There's 2 meters by the looks of it. That's 30 meters. That's 100 meters is the wavelength. And visible light is electromagnetic radiation with a wavelength of just under a millionth of a meter. Violet light is low wavelength and red light is longer wavelength. But actually this thing extends a lot further than that. Now this brown line here is where the atmosphere blocks transmission. And this stuff down here is X-rays and stuff, which the sun chucks out in copious quantities. And you know that an X-ray in a hospital, because they all go and hide behind a LED screen, it's dangerous. Right. Well, if if X-rays came straight down to the Earth and the sun, we'd all get fried. So it's just as well that the atmosphere blocks that stuff. But it does mean that if you want to look at it, you've got to go above the atmosphere into space. That stuff's all blocked, so they send up infrared, they're called telescopes, up to there. Radio waves get through, which is why you can listen to a radio, because you can transmit the signal through the atmosphere and it gets to the listener. And this stuff up here is blocked, so we can't see that, but we don't tend to do astronomy up there. So in order to take the radio pictures, they probably used telescopes like that, radio telescopes. And I mean, you might have seen the one in Jodrell Bank in Cheshire, which is pretty big. Well, what they've got in places like the Atacama Desert, and they're just building a huge one in South Africa and in Australia now, is a big array of these things. And that's what they used to take those images showing that bit that came out like that. Some of the other stuff was taken in the X-ray, so they had to send us probe above the atmosphere to take that. And the pictures that the space agencies take of these things are all public domain, so you can download them off the internet, and that's how I did it. But the galaxy itself is above the southern hemisphere. You can't see it from Wales. And so I purchased that picture. How much did it cost? £5 or something like that, not very much, for the visible part of it. And then I combined the images myself.
Brilliant, thank you. That's lovely.
Well, I think I've just learnt where the phrase "a brain the size of a planet" comes from. I feel a bit like a black hole. And thank you very much. Absolutely astonishing talk. Thank you very much.
You're welcome. Right, so let's get rid of these.
So, thanks everybody for coming. There were 50 or 60 of us here tonight, so another fantastic attendance. For those of you that have booked some food, Connor's going to be serving at about 1:45, so it should be ready any time now, so that's great. And anybody else, stick around, have a beer and have a chat. Thank you very much. Bye.